Ooh, geez. Okay, let's get started. Just a couple of quick notes. Are y'all okay with the lights off? Are you sure? Okay. Boy, what an intimate class we have. Look at this small little class we have today. Maybe I won't post the recording today. We'll see what happens. We have 2 days left, and I put up over on this little board what we're going to try and achieve this week, at least our understanding. And these are all in your little formula sheet, but let me just point to this right now. We can do a line integral on a vector field over some curve, right? So we got a vector field, we got a curve in space. That curve may close upon itself, so it might be a closed curve, but we have formulas for doing this. What we are going to learn today is that you can actually take that line integral and convert it to a surface integral. And so instead of integrating over the curve, you integrate over a surface. And then hopefully what we'll do is right now we're going to do this today. Okay, we've already done that. We're going to do this right here. We're going to do what's called the flux. It's the surface integral. So instead of a single integral over a curve, we're doing a double integral over a surface of a vector field. And then what we're going to find out, hopefully next class, is that you can convert this surface integral into, now that's this right here, into a triple integral over some solid E using this formula. So this one right here is called Stokes Theorem, and this one right here is called the divergence theorem. Those are the two things we're going to try to achieve. Yes? Yeah, they're on the formula sheets. Okay? That's our plan. Your mini test, I graded all of them except number 7. Number 7 is taking me a long time to get through. So just give me another couple of days, all right? Okay, so we need to pick up where we left off. Where are you? Come here. We were starting with oriented surfaces, right? That's where we left off. But before I do that, I have something else I want to address with you that we did not talk about before. We'll use it today. Remember when we were coming up with the whole idea of parametric surfaces? And we said, I gave you all these different examples. Remember that handout I gave you? And we said we tried to keep on defining, okay, what if you have a disk or a cylinder? How do you define these? Well, the one thing we never talked about was a plane. And I never told you what the parametric equation for a plane would be. Now, we know the general equation of a plane back from way in the beginning of this class, chapter 10. If someone gives you the general equation of a plane, it could be written this way. Remember that? What's ABC there? Components of the normal vector, right? X naught, Y naught, Z naught is a point on the plane, right? The problem with that is an equation, right? What I'm talking about is, can we still draw a plane using one of these, R of UV? Can we still do that, right? It makes sense. Plane's pretty simple, isn't it? We should be able to draw a plane. So here's the idea. If you take a plane, which is just a flat sheet like this, right? If I have a point on that plane, I can actually refer to that as a vector that points to it, right? We call R naught. And then to create the rest of the plane, all I have to do is take any vector on that plane. So let's just say that vector lies on the plane. Okay, call it A. But make sure you understand that vector lies in that plane, all right? And then take any other vector, as long as it's not parallel to A. Okay, so take any other vector. Doesn't even have to be the same length. We'll call it B. And as long as that vector also lies in the plane, so you have two lines in a plane, then, who are my linear algebra students? Y'all taking linear algebra now? No? I thought we had linear algebra. No? Didn't you do linear algebra? That's right. Okay. So if you have two vectors in a flat two-dimensional space like this, and you take every multiple of each vector, you should be able to draw the entire plane. Right? Remember, if you have a point and a vector, and you take all the multiples of that vector, you draw the line, don't you? You draw every line? Or you draw the entire line? Let me see. If I extended this A out forever, I would draw that line, wouldn't I? And if I extended this B out forever, I draw that line. And if I take every, here's technical word, every linear combination of those two vectors, that means I add, let's say if I add those two vectors together, right, parallelogram rule, I would wind up on a point out here, and that would also be on my plane. And if I take, let's say, half of each vector and add them together, I'd be here. Something like that. So every linear combination of those vectors added to the initial vector should give me the plane. So here's the formula. R of u v equals the initial vector r naught, that's like the point on the plane, plus u a plus v b. Now u and v are what? They're my parameters, right? They're just numbers, right? And in this case, I would just say u is in R, u is an element of R, v is an element of R. So they're just real numbers, right? Let u be any number, let v be any number, or all numbers, and you should draw out the entire plane that extends in every direction. Do y'all remember the couch potato formula I told you about for a line? Parametric equation, vector equation of a line, u plus tv. What was our vector equation for a line? It was r naught plus tv, right? So this is what draws a line. Agreed? We did that way back when. All we've done to this is we've replaced my v with what? A. Replace my t with u. So if we ignore this part right here, that's a line, right? And then this VB gives me the other line, and when you add them together and take all combinations, you get the plane. I hope that makes sense. Scalars. They're just scalars, yeah. It's every scalar multiple of these vectors. And of course, if u and v are 0, right, then you're just sitting right there at that point, which is on the plane. So you have to have this. If you don't have this, then your plane is not necessarily going to pass through that point. Okay, that's our first little order of business. Now, let's get on to today's notes. So we talked a little bit about this last time. We talked about this idea of an oriented surface. So if you have a surface, which in this case I'm giving you a sphere, and I got all off track with the Mobius and Klein bottle and all that stuff. Sorry about that, but we're at the end anyway. If we have an oriented surface, then we should be able to compute the normal vector. The normal vector, I have it in the notes. I'll refer to it. It'll come up here in just a second how we compute a normal vector. But we have what's called the positive and negative direction or orientation. Okay. There's two orientations possible, positive and negative. So if I take the, compute the normal vector and it pops out, that would be positive. If it pops in, that would be negative. Well, we're going to have to be very careful. For example, let's go back to this simple idea of a plane. Okay? If I just take a plane, how do I get a normal vector for a plane? I can get like two vectors on it, right? And I can cross them, and that'll pop a normal out, and that normal will be perpendicular to the plane. Agreed? But if I crossed them the other way, wouldn't it pop that out the bottom instead? So which one is positive, which one's negative? See here, with the sphere, it made sense that positive would be out and negative would be in. Here, we don't have that necessarily, do we? So we will need to address this, and we will cross this bridge when we get to it, all right? But there is some ambiguity here. We need to kind of agree on what positive is going to be for us. Make sense? Okay. So now, How do we compute the normal vector of an oriented surface? I need to talk about this a little bit more. There's some wording in here I need to talk about. An oriented surface is a two-sided surface in which the normal vector at every point on the surface exists and such that the normal vector varies continuously over the surface. So all this is saying is that if you have some surface out there, if it's going to be what's called an oriented surface, that means that at every point there is some normal vector, right? And then as you move across the surface, that vector changes continuously. Continuously means that there's no like crazy jump. Like it's not like this, and then all of a sudden you get to here, and then boom, it pops off the other side. If it's going to change, it's going to slowly change or continuously change. Does that kind of make sense? It's math language. That's right. So now I'm not going to give you something that's not oriented, all right? But we need to make sure we understand what that definition means in some way, in some sense. Okay, so if you have an oriented surface, here's how we compute the normal vector. You take the cross product of the partials. Okay, so assuming that the surface can be drawn with a vector, with a parametric equations, then you take the partials, you cross them. That should give you a vector popping out perpendicular to the tangent plane. And then you divide it by what? Its own length. That gives it a length of 1, doesn't it? Okay. That would be what we call n. And then if we take the opposite of that, negative n, then that would give us the one in the other direction. Now, the special case when the surface can be expressed as z equals g of xy. So I want to show you where this normal vector special case comes from, all right? So that's what I'm going to do now. Let's say that we have a surface where z is a function of xy. Then I could convert this whole thing into my parametric surface like this. My x I'm going to call u, my y I'm going to call v, and then my z is some function of u and v. Understand what I did here? I said, all right, z component is a function of x and y. I'm going to switch x and y to u and v just so it matches the u and v that we've been using the whole time. If I take the partial of that with respect to u, I get 1, 0, and then isn't it the partial of g with respect to u? And then if I take the partial with respect to v, I should get 0, 1 partial of g with respect to v. And now if I say cross those, what do? We cover up these two, right? And we do that little here to here, here to here, right? So what would we get? 0 times this is gone, minus partial g with respect to u times 1. So I would get this cross product is partial, negative or positive? Negative partial g with respect to u. And now we do the j component, so we cover up j and we go 1 times this, but then it's opposite, right? So negative partial g with respect to v. My computer's acting really weird. Partial g with respect to v. And then what about the other part? 0, right? So that's not there. And then if we do the last one, the k component, this just gives me 1 and then nothing. So I just get 1 there. Yes? So going back to the notes, which I did what I always do. It's going to be my summer project, trying to figure out why in the hell that happens. Do y'all see how that matches the formula now? Okay. Okay, so we get this. And then what's this right here? That's the magnitude of that vector, isn't it? Okay. So that's in the special case that z is a function of x and y. What about if it was a case where x was a function of y and z? Do you think you could do something similar to this? And we will, all right? But this is just to get us warmed up with that. All right, close-oriented surfaces. So if the surface is closed, that means it encloses some solid E, then positive orientation is the one which the normals point away from E. An example is the unit sphere. Okay, so closed surface, it's kind of like back here with curves. We had curves and we had closed curves, right? Here we have surfaces and then we have closed surfaces. Do y'all remember that? When we had a curve and it was closed, do you remember having a positive and negative orientation? Positive was counterclockwise, negative was clockwise. Well, now with a surface, we have this positive and negative orientation also. Positive means out of the surface, negative means into the surface. Got it? Let's see here now. This is the big idea of this end of this section, which is the surface integral of f over s, which is also referred to as the flux. And I showed you all this picture at the end of class. This is the big notation, though, that we need to see. Double integral over s, where s is our surface, of the vector field dotted ds. Now, the s here, notice, is a vector s. And what this turns into, at the end of it all for us, and I'm not going to go through the proof of this. It's in the book if you want to read through why this is true. This turns out to be the double integral over d of f dotted with ru cross rv. Now, what's ru and rv here? The partials of the surface, right? R is still our surface. D is what? Kind of, yes. It is a region, but what? Wasn't D our restrictions on U and V? Remember, U lived between two things, and V lived between two things. And so D is that domain of the parametric surface function, right? Y'all okay with that or not? If we want to draw a sphere, we used like U and V and all these cosines, sines, right, and all that. And we let one of them live between 0 and pi, the other one between 0 and 2 pi to draw the sphere. Our domain for a sphere would be 0 to pi, 0 to 2 pi. Okay, I showed you this. This was just visually trying to understand flux. I don't think I want to go through it again. Is that all right? Okay. Let's just get to computation of flux. All right, so here it is. Since you have that in your notes, I'm going to go straight to a blank page. Example 3. We are trying to compute the flux with the vector field given as y, z, x on the unit sphere, right? Where's my problem? Across the unit sphere, right? So we have a vector field, we have the unit sphere. I'd like to compute flux. So that means I need to know that the formula that I'm going to go for is this one, which turns out to be the double integral over d of f dot the cross product of the partials of my surface dA. So that is today's formula right here. And that's in your formulas, right? Do I have that written in there good? I should have numbered these or something. It's all here though. Now, just to be clear, if you look at the formulas that I had up here for flux, there's this one right here, f dot ds, and then there's this one. Look at this one in the middle here. F dot n ds. And notice the difference here. Here, this was just ds, and the s was a vector. Here is the normal times ds. Here, s is the surface, not a vector. So the way you look at this is this. These are the infinitesimally small surface areas, and they are scaling the n, which is the normal vector. And you're dotting that with your vector field. Is this an operator? It's scaling. It's not changing. Yeah. This here, this right here is the way that we write this. So this is purely notation. This means this. You have to go back to my other video where I was trying to explain flux. You got a vector field in three-dimensional space. You have a surface. You have a normal. We take the vector field, we project it onto the normal, and then we add those up. And that gives us our flux. Okay, so the reason I want to bring this up is because I'm going to refer back to this as we move along. It's not going to be in this example, but later on. All right, so if I'm going to do this, I need to know what R is, right? So what's R? It's the unit sphere, right? And the formula for unit sphere will be, we've done this, used it several times, sine u cosine v, sine u sine v, cosine u, and here u is between 0 and pi, v is between 0 to pi. I need to take the partials. We've done that before, haven't we? I need to cross the partials. We've done that before. So here, let me just write down what our crossed partials are. I don't need magnitude though, right? Right, in the formula, I don't need the magnitude of the crossed partials. So the crossed partials is s sine squared u cosine v, sine squared u sine v, and then cosine u sine u. So I'm not showing that work, right? But you could do that. And now what I need to do is I need to take this vector. I need to dot it. That's a dot up here. I need to dot it with the vector field. Now the vector field is yzx, right? But whenever we just write f here, what we really mean is f evaluated where? On the surface, right? So I need to basically evaluate f at r, which means I'll replace my x here with what? The x component, sine u cosine v. I replace the y here with sine u sine v, and I replace z with cosine u. So let's try and do this. I'll write it down a little slower here. F with r of uv inside of it would become the vector, you tell me. What's y? Sine u sine v, okay. I'm just plugging in right now. Sine u sine v. And then cosine u, and then sine u cosine v. And I'd like to dot these two together, right? Dot those two. I'm ready to set up the integral. I'm just going to write it down. It's double integral over d. Let's write the dot product in there. So what's the dot product going to give me here? Not cross product, dot, right? So all I'm doing is multiplying these together, adding these two multiplied together, adding these two multiplied together. So sine cubed u sine v cosine v plus, right, not a vector here, plus sine squared u cosine u. I think my computer is has had enough this semester. It doesn't want to do anymore. It's really lagging here on my writing. And then finally, plus, yeah, I've got a sine squared, right? U cosine V. All of that dA. Now let's talk about D. D is the domain of my surface, which right now the parameters I'm using are U and V. So whatever the restrictions on U and V were, and they're right here. They're constants, right? So ordered here it won't matter. And so without having to go through all this again, I'm just going to scratch this D here, make it 0 to pi, 0 to 2 pi, so I don't have to rewrite all that. And then out here, this would become, this order does matter, D, which one went from 0 to 2 pi? V, right? So dV, du. Now what you can do at this point is you can look at this as 3 separate integrals, right? The first integral has u's, and then separated from it, it has functions, well, functions of u separated from functions of v by multiplication, which means there's that property we can split it into 2 different integrals and multiply the answers. So I'm not going to do this whole thing because we don't have time for it, but I'll just set this first one up. I'm going to say, I'm going to have 2 integrals. One's going to go from 0 to pi. The other one's going to go from 0 to 2 pi. Here's multiplication right there between them. 0 to pi is on the variable u, isn't it? So I'm going to put sine cubed u du here. And then on the other one, it's the v, so sine v cosine v dv. And then I compute those and multiply the answers. I do the same thing here. I do the same thing here. Okay? If you do all that, you should get 0. What will happen is you'll get antiderivatives in there that have sine in them, and then you're evaluating at 0 and pi, and then sine of 0 is 0, sine of pi is 0, so you wind up getting 0, right? So the flux would be 0. Is the flux on a sphere always 0? Well, it depends on the vector field, right? For this particular vector field, it's 0. Net, yeah. That means the flow out and flow in basically is 0, net flow. Sure. Yeah, if it said top half of sphere, it may not be 0. Or first octant maybe, may not be 0. Actually, it wouldn't, because just think about, the reason we're getting 0 here is because the 0 to pi here. If we change that, we're not going to have that issue, and so we'll have answer. Okay, let's move on. All right, I actually have a typo in my notes here that I'll fix. Well, yeah, it's a typo. All right, let's talk about flux whenever we have 3 special cases. The book only talks about 1, but I'm going to talk about all 3. All right, in the case where z is a function of x and y. In other words, our parametric surface can be written as a surface where x and y, the z-coordinate depends on x and y. So if that's the case, then we get this formula right here. And what I'm going to do is I'm going to derive that formula because it doesn't take very long. You ready? Okay, let's say that z is a function of x and y. Then I could rewrite r of uv to be uv g of uv. I just did this a second ago, didn't I? Yes? Then we took the partials and crossed them, didn't we? And when I did that, I got negative partial g with respect to u, negative partial g with respect to v. Man, what is up? Feels almost like that one spot right there. It doesn't want to write on it. My ink's running out. And 1. All right, that's what we got. Now, if F is some vector field, which I'm going to act like I don't know what it is, so I'm going to call it PQR. Right, those are components of the vector field. Then when I dot those two, what do I get? When I dot them, when I do F dotted with R, U, cross R, V, I get, no, sorry, not a vector. I get what? This times this, right? This times this, and then finally this times this. Agreed? And that gives you part of this formula. It's negative P partial G with respect to V, and then plus, but then there's minus, so minus Q partial G with respect to, wait, that was a U. V, and then plus R. Do you all agree with that? Okay, so going back to the formula here, that's what this is saying. Instead of having to go through and do this, and they used X and Y instead of U and V, really doesn't matter. In my development of it, I switched all my X's and Y's to U's and V's. They just leave it the same here. So here's what we'll have, okay? This formula right here. And then, we're doing it over the restrictions on X here, X and Y, because we're switched. They leave everything as X and Y. So if this D here is the, your bounds on X and your bounds on Y. Now, there's something very subtle, and this is where there was a mistake in the notes. I want us to talk about the normal vector here. Okay, here I said, this is the formula if the normals of this surface point up and out the z-axis. So let me go back to this here. When we computed this cross product, doesn't that give us a normal vector? It's not unit length yet, right? Because we haven't divided by its length. But that vector is pointed, it has an x component, a y component, and a z component, right? So it's a vector somewhere. Since this surface is a function of x and y, we look at it like a sheet of paper. That normal vector is sticking out somewhere. Look at the z component of it. What is it? 1. So no matter what the x and y component are, the z moves it up 1, which means this is pointing up above the surface, isn't it? And that's why I put here this formula works, right? This is the formula if the normals you're looking at are pointing up. Not straight up, but up as opposed to down, okay? That makes sense? That's going to be super important as we get to this formula right here, all right? When we get to this, you'll see why that's important. Next, look at this one. What if your surface can be written where x is a function of y and z? Now, if you look at your notes, is the formula that you have the one that's up on the board? I had put, oh yeah, no, it's the last one that was off. Never mind. The middle one matches up with what you have in your notes, right? P minus Q partial G with respect to Y minus R partial G with respect to Z. Now, the way we get that, and I think it's important to walk through it quickly, is that this time X is a function of Y and Z, right? So if I rewrite this R of UV, I can call each component, how do I do this? Why don't we let U be Y and let V be Z? Is that okay? So my Y is going to be U and my Z is going to be V, is that all right? Then what's my X? It's some function of Y and Z, right? G of YZ. And now when you take partial with respect to U, what do you get? partial of g with respect to u. What's the derivative of the next one with respect to u? 1, right? And then 0. And then if I do partial of r with respect to v, you get partial g with respect to v, then what? 0 and then 1. And now take their cross product. What's the cross? Well, cover this up, right? And do that thing. You'll just get 1, won't you? Cover up the middle and do this, and then subtract. So this times this, that gives you the partial g with respect to u, but then make it negative. Negative partial g with respect to u. And then finally, cover up these two. Here to here, 0, here to here. We're supposed to subtract it, so what, negative partial g with respect to v. And then what would happen if you dot that with f? Well, you get this, don't you? F is PQR. Dot that with this cross product we just got, and you get this formula. Now, I put here, and it's not on your notes, normals pointing toward the reader out the x-axis. So going back to this computation we just did, look at your x component. Your x component is positive, right? So three-dimensionally speaking, it's coming at us, right? If we draw it, let me help by doing it this way. If we draw like this, if this is x, this is y, this is z, then those normals that we're getting here are going to be coming out this way towards the reader. Now they won't be straight out, but that, you know, the x component comes towards us as opposed to going away from us. Does that make sense? In the previous example I just did, it was like this. X, y, z. We know our normals, the z component pointed up some. So that's what you're saying, going up the z-axis. Okay, now the last one is the one where I had a mistake on the formula. And it's not necessarily a mistake. I just never pointed out where those normals were pointing. So what if we have y as a function of x and z? Y is a function of x and z. Then I can rewrite this as r of uv equals, well, x will be u, z will be v, and my y is some function of those two. Partial r, respect to u, 1. Partial g with respect to u, 0. Yeah? Partial r with respect to v should give me 0. Partial g with respect to v, 1. Cross them. Okay, when we cross them, cover up this one. We do this, right? And we should just get partial g with respect to u. Cover up the middle, we should get what? 1 times 1, but aren't we supposed to subtract? And then 0, so this will be negative 1. And then partial g with respect to v. Now, if I dot that with f, right? If I take f, which is PQR, and I dot them, I get the formula that appears in your notes, don't I? Yes? What appears in your notes? P partial g with respect to x minus q, right? Plus r partial g with respect to z. Now, that's not incorrect, but I want you to change it because think about this right here. Look at this y component. Which way is this y component pointing? In the negative direction, right? All the others were pointing to the positive. So if we are looking at it like this, this is x, this is y, this is z, everything I've done up to this point, I've made it so that the normals have worked out to always point out in the positive direction of the axes, right? So right now, the way this formula is working, these are pointed in the negative y direction, aren't they? I would like to have a formula that works for when it's pointed in the positive y. So all I need to do is scale this by -1, which points it in the other direction, doesn't it? So what I've done is I've made this negative, this positive, this negative. Then I dotted it with f. And then I get this formula down here, but change. Whoa. Yeah, this is it. This formula, but change. So what I want you to do is change it to this. Negative, right, here. Make that one a positive. Make that one a negative. And then make sure you make a note that the normals of here, for this formula to work, the normals are pointing to the right out the y-axis. Does that make sense to everyone? No? To the right, this way. If the formula, the way it appeared before, they were pointed to the left, like this. Here's the y-axis. This is to the left, right? This is to the left, correct? And then going this way would be to the right. Yes. Yes. That's right. Positive, negative, positive. No. I'm doing that other one. The other shortcut. Yeah, so yeah. Okay? So in the event that any of the surfaces can be written as functions of one of two of the variables, you will be able to use this shortcut. Okay, here we go. Let's do this example. Find the flux of the vector field f of x, y, z equals xy, yz, zx across the surface S, where S is the part of the paraboloid z equals 4 minus x squared minus y squared that lies above the region x between 0, 1, y between 0, 1. Use upward orientation. So here's a picture, right? We have a paraboloid. I've cut it off so that if you look from the top, it's on that, what is that, a rectangle? It's the part of the paraboloid above this rectangle. And there's some vector field sitting here in three-dimensional space. And there's the surface, right? And so you got this vector field acting on the surface, and you want to know basically the flux, which is like the amount going in or out of the surface. Yeah? So we have the F, right? Do we have a parametric surface? We do, right? But it's even better than that. I can determine z by just knowing x and y. So z is a function of x and y, isn't it? So I can use the formula that we just had. Y'all see that? That's why I gave you what we just looked at. So let's work through this. So first thing, I'm going to write down z is equal to 4 minus x squared minus y squared. Let me write down the vector field over here. It was PQR, which is XY, YZ, ZX. The formula that I'm going to be using, because Z is a function of X and Y, right? The formula that I'll be using is double integral. Let me write it this way. The flux will be equal to the double integral over d of, you tell me which formula I'm using. You can just say what's in there if you want. Okay, which for us will be what in this case? Like, do we need to actually find R and cross it? Do we need to figure out what R is, and do we need to cross it? Look at what this formula just said right here. It said, look, if you can express the surface at Z as a function of X and Y, then you don't have to do this. All you have to do is take, negative p times the partial of g with respect to x minus q times partial of g with respect to y plus r, right? PQR is just the vector field. See, this eliminates all that crossing that we'd have to do. But we also have to make sure the formula is being used correctly. This is if we want our normals to be pointed up out the z-axis. What did I ask for in this problem? Upward orientation, meaning up is positive, okay? And that's what we have with that formula, right? Up is positive. So I will use that formula exactly. So I'll go ahead and write down, I'm using negative p partial g with that's not a g. Partial g with respect to x minus q partial g with respect to y, and then plus r. All right, what is p? P is xy. What is the partial of g with, I forgot my negative sign out there. What is the partial of g with respect to x? Negative 2x. Gosh. Okay, and then minus what's q? yz. And what's the partial of g with respect to y? Negative 2y. Okay, plus r. What's r? zx. All of that, dA. Follow? If you like lines, then here are some lines. Negative p, partial q, partial r, right? That's where everything came from. Let me try and clean this up a little bit. I'll get my limits of integration in there in a second. This is 2xy, x squared y, plus 2y squared z plus xz dA. My two variables that I'm using here are x and y, right? Those are the ones that are going to make up my domain. Do you see the little issue we have still in this, though, we have to resolve? We have to get rid of the z, right? But z was 4 minus x squared minus y squared. So now what I need to do is replace all those z's with that. Double integral d 2x squared y plus 2y squared, and now replace z with 4 minus x squared minus y squared, and then plus x times z again, which is 4 minus x squared minus y squared dA. I have everything in terms of x and y now, don't I? So the last thing to do is what? I mean, not last thing. For the setup, what's the last thing? The integration. But you need your limits of integration, don't you? Do you know your restriction on x and y? 0 to 1. 0 to 1 again, right? At the end here, I'll have d. Does it matter? In this case, it doesn't, because they both go from the same thing, right? 0 to 1. And they're both constants, so order of integration doesn't matter. And then the inside of that is all that junk simplified, right? You could like multiply through and collect like terms. I'm not going to go through all this. This is going to come out to be exactly 713 over 180, which is approximately 3.96. Positive flux. More going out than going in. I guess if that's the way you want to look at it, okay? The book equates it to like, it all depends on what the vector field is. That determines what the physical, interpretation of this is. But the book talks about, if you have like a mesh, like a net, and you have water flowing through it, it's a measurement of how much water is going through it. Or if you want fish going through this little area, and a fish coming the other way. Net-wise, what's happening? 3.96. Heat transfer, yep. I was going to try and do one of those. heat transfer problems. They're pretty good. All right, let's take a look at a different one. This one's interesting. It's hard to tell from your notes, but what we have here is we're trying to find the flux. Let me see, which one is this one? We're trying to find the flux of a vector field given by 0, y, negative z across the surface S, where S is the part of the paraboloid y equals x squared plus z squared, with y between 0 and 1. And the disk, x squared plus z squared, is less than or equal to 1 with y equals 1. So this surface is actually two surfaces. It's this paraboloid that opens sideways out the y-axis, and then there's this disk on the front of it. So it's like a bowl sideways with a cover on the bowl. That's an entire surface, right? So what I need to do is look at the flux over each piece, each of the two surfaces, and add those up. Make sense? Now, we need to try and understand what positive orientation is here. What did we say earlier in the notes? Right here. If the surface is closed, is our surface closed? Then the positive orientation is the one in which the normals point away from E. Right? Away from E. That's the solid that it encloses. So when you look at this solid, looking at this disk right here, right? The normals that we want point which way? To the right, right? Down the y-axis like. And then the part of the paraboloid here, which way do those normals point? Down the left. That's critical because our formula, right? Our formula that we just derived, if we could write y as a function of x and z, we can use that formula if the normals point to the right. Our normals on this surface here do not point to the right, they point to the left. So we're going to have to change the formula a little bit. Just scale it by -1, but that's, I mean, it has to be done though, okay? All right, so, sorry? Oh yeah, they're definitely useful. And anytime we need to change the orientation in the opposite direction, we just multiply by -1. So let's work this out. Let's call, draw my picture here. Let's call this one S2. We'll do that one second. We'll do this one first, S1. Is that all right? Yeah, well, S1 is just what? How far out is S1? It's 1, right? So that does have an equation, right? It's y equals 1. You agree with that? That's right. It's not. So let's try and figure out how we're going to do this. What we're trying to do for S1, that's all I'm doing right now is S1. I'm trying to do this over S1 of F dot ds. We have several options. Let me give you one option, okay? Can you define this surface right here? Can you define it with a vector, as a parametric surface, R of something? Well, it's a disk, right? Okay, go for it then. What is it? R view V is, what is it? V cosine U. How far it is? 1. And then V sine U. What's V between? What's U between? Zero to 2 pi on U, and V is 0 to 1, right? Does everyone agree that that parametric surface right here draws that disk, which is S1? So now what would I need to do in order to figure this out. I need partials. What's the partial with respect to u? Negative v sine u, 0, v cosine u. What's the partial with respect to v? See, cosine u, 0, sine u. Y'all agree with that? What's their cross product? Zero's the first component, right? How about the next one? You get v sine squared u plus, which is, well, minus, but then it gets changed, so it is plus, isn't it? Plus v squared cosine squared u. I don't know why I did v squared. Sorry about that. And then what's the last one? 0. Which, isn't that inside just v? Sine squared plus cosine squared u. Right, factor out of v. Now I'm supposed to dot that with what? The vector field. Now, what was my vector field? Okay, I'll write that down up here. We're still working on S1, right? My vector field was 0y, negative z. I'm going to dot that with this thing down here. So what's f when we evaluate it on that particular parametric surface? 0. So it's 0 because 0, right? It's the y coordinate of my parametric surface, which is what? 1, right? 1. And then what's negative z? Negative v sine u. So double integral over s of f dot ds is equal to double integral over d of f dotted with ru cross rv. So dot these up. Dot this, and what do you get? 0, v, and 0. So you just give v? Shit, man. All that for v. And then dA. Okay, what are our restrictions on our variables here? V is 0 to 1. U is 0 to 2 pi. We're integrating v du dv, right? Agreed? Antiderivative of v with respect to u. Isn't that just uv? Yes, uv evaluated from u equals 0 to 2 pi. Are y'all still with me, or plug in? We're plugging in 2 pi for what? For u, so we get 2 pi v. And then plug in 0, it's gone, right? 2 pi dv. Antiderivative of 2 pi, just 2 pi v, right? Evaluate 0, 1. Our answer is, hold on. Oh, we're 2 pi v. Sorry. Yes, thank you. I was just going to, I was just going to do that and be like, well, how the hell is it not matching my answer? It's 2 pi v here, right? And then 1/2, so it'll just be pi v squared, evaluated 0 to 1, which is pi. Okay, that, my friends, is the hard way. All right, now you want to see the easy way? It was a lesson. It's a lesson to just show you working hard versus working smart. Okay, let's go back to this formula right here. Well, yeah, I'll do it this way. Look at this right here. What is F dot N here? Come back over here. Tell me about my normal vector on S1. Pointing out y exactly, right? It's actually the vector, what? 0, 0, 1, isn't it? I mean, we don't even have to do any computation because of the way things were oriented. Everyone could look at this and just say, hey, look, that normal vector right there is 0, 0, 1, isn't it? Oh, sorry. 0, 1, 0. You know what I mean? Same thing. No, it's not. But you know what I mean, right? That's just that vector pointed out to the right, isn't it? Now, we could have seen that if we would have just divided this by its own length. Right? What's this divided by its own length? 1. Okay. But how does that help me do this problem a little quicker? Well, here's how. If I go like this, and I know that this vector right here is, what was my original vector function? 0, y, negative z. God, I need to do like a reset on my computer. 0, y, negative z, right? And I want to dot that with that vector, 0, 1, 0, ds. Then what do I get? I get y, don't I? Now, what is y? If you're on that circle, right? If you're on that disk right now, if you're on that disk, where are you? What's your y value? 1. Okay? Now hang tight. We have to convert this to a double integral. So it's a polar region, right? So now what I'm doing is I'm looking at this thing and I'm saying I'm trying to do a double integral. Here's what I'm trying to integrate. I look at its shadow down on the ground, or on the ground. It's actually on the xz plane, right? Isn't that a circle? So this converts over to be this, the double integral over that circle, right? How can I write that circle? Well, I'll just write a d first, and I go 1 what? dA? Is that okay if I write it like that? Can anyone tell me what the answer to that is? What's that? Yeah, but why? That's right. What is the double integral of 1 dA over the region D? It's the area of the region, isn't it? What's the area of that shadow on the ground? Pi r squared. What's its radius? 1. So our answer should have been just pi. See? No work. Do y'all see the difference between the two approaches? Much faster this way. And that's what you should be looking for on these problems. You'll see in the next example and a couple more down the road, is that whenever you have surfaces that are parallel to one of the, like the xy plane or the yz plane or the xz plane, then the normal vector is always going to be either 1, 0, 0 or 0, 1, 0 or 0, 0, 1. In that case, we want to use this, or at least be aware that we can use this, instead of finding what R is and then trying to find the cross product and you know, that's too tedious. Gives us the same result. Okay? Now, we've only done S1, right? I need to do S2. Here's S2. So let's go for S2 now. So far we're at pi, right? S2. Well, S2, we said that S2, the y-coordinate, x squared plus z squared, was this paraboloid, right? Which means I can write y as a function of g of xz, right? And according to the formula, the flux over this surface S2 of f dot ds should be equal to double integral over d of, so we go to our formula, right? And we're using the one for y as a function of xz, except that our normals are not pointed to the right the way that this formula works, right? So we need to point them to the left. To point them to the left, all we do is multiply this formula by -1. Is that all right? Everyone understand why we're pointed to the left? Look at our surface. It goes like that, right? The normals on that S1 were this way, pointing away from the solid it encloses. The normals on that paraboloid thing need to point away also, which means that the y component of those green vectors must be negative, which means that in our formula, the y component cannot be positive. It's got to be negative, so you have to change everything. So I'm using this formula instead. P partial g with respect to x, minus q plus r partial g respect to z dA. All right, what's P? Wasn't it 0? So that kills off that first piece. What's negative Q? Negative Y. And then we have plus R, which was, R was negative Z, wasn't it? R was negative Z. And then times what? The partial g with respect to z, which is 2z. All that dA over d. Let's clean that up a little bit. Double integral over d of negative y minus 2z squared. No, yes. Now what? You know y is 0 to 1. Now what's wrong with this though right here? Or is there anything wrong with this? Look, yeah, we need it in terms of x and z, because look, like before when we had z's in the problem, we had to get rid of them and use that. Remember, we used 4. We had a problem just before this that was z was equal to 4 minus x squared minus y squared. We replaced all our z's with 4 minus x squared. Here, y is the one that is a function of x and z. So we need to replace all our y's with x squared plus z squared. So I'm going to replace all my y's with x squared plus z squared. So doesn't this turn into negative x squared minus z squared And I said minus 2z squared dA. Now I can try integrating this because the two independent variables that we had to start the problem, right, appear in my integrand. However, when we come back up here, we look at that. If we're trying to do a double integral under this paraboloid, and we're doing it on a circular region, we want to convert this to polar, don't we? So at this point, we want to go polar. Every time I say go polar, I think go postal, not polar. Remember that saying, go postal? No? You've heard that before? It's not too funny nowadays, is it? All right, so tell me about this. If we convert to polar, right, we're trying to project that circle onto the XZ plane like that, right? That circle? I don't like that circle. Right, that's on the XZ plane. It's just a unit circle. So here are the parameters that will change. We'll let our x be equal to, how about r cosine theta? We'll let our z be equal to r sine theta. We'll let our r go ahead and vary between 0 and 1. We'll let our theta go between 0 and pi, 2 pi. Now what's great about that is that the first two terms, right? See the first two terms up there? Negative x squared minus z squared. If you take a negative out of just these two, isn't that going to be a negative sitting here and then x squared plus z squared? What's x squared plus z squared? R squared. Just like x squared plus y squared used to be r squared, now it's x squared plus z squared. So that'll become, I'm ready to switch this integral over. I'm going to go from 0 to 2 pi. I'm going to go 0 to 1. That first thing turned into negative r squared. Now what about 2z squared? That's going to turn into 2, what's oh wait a minute, yeah, what's z? It's r sine theta, so square it, so r squared sine squared theta. Close it off. Right, we got that? Oh. This right here, factor a negative out, that became this. And then minus 2, and then this is z squared. Yes? What else? R dr d theta. That's right. Don't forget the r. Because you went to polar, didn't you? You went to polar. Now, if you compute all that, which I'm not going to, you get negative pi. Which kind of sucks, because doesn't that mean the answer is 0? Yeah. Nah, except for on the test, right? So the flux over S of F ds is 0. Let's see, I want to go back up here and change this. Some of my notation's a little bit bad up here. I'm doing this double integral over S. This should, S2, that should actually be an S2 there, right? And this one should have been over S1. But I think you're okay, right? Two different surfaces. All right, good. Okay. Find the flux of the vector field, blah, blah, across the surface where S is the boundary of the solid half cylinder. So look at this here. Here's your cylinder. It's been cut in half, right? This green part is governed by this right here, this square root, basically. This front part, your x value out there is 2. So it's like a half circle, x value 2. The back part of it, half circle, x value 0. Bottom of this thing is a rectangle, right? So remember what I just said about working hard and working smart, right? Look at this front side right here. Which way is the normal vector pointed on this front side? 1, right? And what's positive orientation for us here, for flux? Everything going out, right? Away from the solid. So coming off this front end here, I'm going to want my vectors, my ends, to come out, which means that the ends are what? What's the vector for n here on this entire front? 1, 0, 0. On the back side, what's the n? Negative 1, 0, 0, right? What about coming off the bottom? 0, 0, negative 1 pointed straight down. Now, the vectors coming off this cylinder, right? That cylinder is a function of what two variables? Or is it really even a function of two variables? This right here, the green. Yeah, what two variables is it a function of? X and Y, because you can look at the XY plane as being the floor and then cast everything up into the surface. So what do the normal vectors of this look like? They should point away, right? And don't we have a formula for that? Our formula, they point up. So if Z is a function of X and Y, the formula we have will work for this part. So we have 1, 2, 3, 4 surfaces. The 3 surfaces that are flat, parallel to the coordinate planes, should be easy. The green one is the one that's going to take maybe a little work. So let's start with the flat ones, okay? Y'all follow me on this? Okay. We'll see. Let me draw this thing. There, 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 there. Let's call this one S1 in the front here. That back side, we'll call it S2. The bottom side there, call that S3. And then we'll call this one S4. So let's compute the flux over S1. I'll try and get my notation a little better here. ds1, right? That's equal to, according to the formula, the double integral over S1 of f dotted with the normal vector, right? What's our normal vector on S1? So I'll draw it too. Look, here's our normal vector off S1. That normal vector is the vector 1, 0, 0. And then ds1, but without the vector. That's our surface area infinitesimal. Now, the vector field, I didn't put it here, but I'll put it up here, PQR. Our vector field for this problem is, oops, wrong section. X squared, y squared, z squared. So if I take that f and I dot it with 1, 0, 0, all I'm left with is what? X squared. ds1. Can anybody tell me what magic we're going to do now? Not magic, but does anyone notice something? When you're on S1, there's something very special that's happening when you're on S1. What's what? It's a half circle, but there's something else. Look at our integral. What do we have in our integral? Our integrand is x squared, right? X is constant there, isn't it? What is x when we're on S1? It's 2. Remember in here, x was between 0 and 2, so x came out to 2, right? So if we're on S1, x is always 2. Well, ain't that great? Because if x is 2, this just becomes double integral over d of 4 dA. Right? It's just a constant. And what if we pull that constant out, double integral over d, 1 dA, what's that? The area, right? What's the area of S1? It's half of pi r squared. What's the radius of that circle, S1? Or that, it's the radius 1, right? So isn't that S1 has an area of pi over 2, but then times 4. So you get 2 pi. So this is 4 times pi over 2. That's how we get that. This is the area, right? This is the area of S1. Okay, can anyone tell me about S2? It's 0. Exactly. Now let's see why it's 0. I'm going to work it in right here. On S2, if we want the flux over S2 of F ds2, then we need the normal. The normal coming off S2 going backwards here was what? Negative 1, 0, 0. So I can do double integral for S2 of F dotted with negative 1, 0, 0 ds1. But that's just going to turn into double integral S2 of negative x squared, right? ds1. But because we're on S2, S2 was 0. X is 0, right? On S2, that backside, the x coordinate is always 0. So this is just 0 because this is 0. X is 0. Yeah, I am. Just to confuse you. Thank you. All right, let's go for S3. Would it be 0? Probably. Let's see why. On S3, let's talk about S3. What's the normal vector? 0, 0 what? Negative 1. And when I dot that with F, I just get negative z squared. But when we're on S3, what's z? It's 0, because it's that plane, isn't it? Right? Isn't S3 sitting on the ground? Like that? Z is 0 there. So this over S3 of F dot ds3 is 0. Is that all right or not? I mean, what if it wasn't? Then we would have to do more work. But, I mean, these problems, some of these surfaces are supposed to not require a lot of work. All right, S4 is the one that's going to take a little bit of doing. All right, so on S4, let's discuss this. On S4, we're just talking about this part, right? This we can look at as z is a function of x and y. What is that function? Square root of 1 minus y squared. Now, even though x does not appear in there, you could say that's a function of x and y. And the normals on this, right, will point up, right? That's what we want them to point up, don't we? The formula we have for this, if we use it, will point these things up, right? So what's our formula? We will go back and defer to right here. It's this first special case, right? Z is g of xy. We want our normals pointing up the z-axis. This is the formula we'll use. Negative p, partial g with respect to x, minus q, partial g with respect to y, plus r. So I want double integral over d of, should I write the formula down? Negative p partial g with respect to x minus q partial g with respect to y plus r dA. This is double integral over d. All right, what is negative p? Negative x squared. What's partial g with respect to x? 0. There's no x. Okay. Minus, what is q? Y squared, right? What's partial g with respect to y? Yeah, so you got to work that out a little bit. You get negative 2y over 1 half square root 1 minus y squared. You get some stuff to cancel out there. You have to do chain rule though, right? Derivative of the square root of something is 1 over 2 times square root of it, then times the derivative of what's inside. So negative 2y. All right, so we got that. And then plus r. What's r? Z squared. All this dA. Let me clean. What do we have there? Y cubed over square root 1 minus y squared. Then plus z squared, but what's z? Square root of 1 minus y squared, right? So when we square that, we just get 1 minus y squared dA. Now let me get my hands around the region here. D is the restrictions on x and y. That's a rectangular region, isn't it? When we come back over here and we look at this, right, this green surface up top, we look at its projection down, we have a rectangle. My x's are between negative 1 and 1. My y's are between 0 and 2. No, other way around. My x is between 0 and 2. My y's are between negative 1 and 1. So I'll go 0 to 2, negative 1 to 1 of all that junk. D. See, x was 0 to 2, y was 0 to 1. You think you could integrate that? Well, I know you could integrate these two. How about this one? How would you try and integrate that one? Trig substitution? Yeah. Trig sub? How many of you would do trig sub there? Yeah. Let's see. Yeah, I just want to mess with that for just a second. I lied. It's going to be more in a second, but I'm not going to take it the whole way. This is back to like a Cal 2 problem here. Like, how would you do that? So I heard trig sub, which I agree with, but I also do like the other suggestion that Luke just brought up, and that's make that y times y squared up there. You're going to call your u 1 minus y squared, Luke, right? You're going to turn your du here into negative 2y dy. And then up here you can solve this for y squared. What would you get? Y squared is 1 minus u. Over here, negative 1 half du is y dy. Ooh, okay, so what am I going to do? Everywhere I'm not going to do that. Everywhere I see y dy, that's going to be replaced by what? Negative 1 half du. Wherever I see y squared, right? That's right here. That's going to be replaced with 1 minus u. And then everything on the bottom is going to become, what, square root of u? So this integral turns into negative 1 half comes out. I have a y on y d. Oh, the y dy is gone. So what's on top? 1 minus u. What's on the bottom? Square root u du. Just turn this into two different terms. U to the negative 1 half minus u to the 1 half. And then just integrate term by term, power rule. Could be done. I just didn't know how many of you had seen something like that before. I just wanted to point it out. What a mess, man. My handwriting is just getting worse with age, I think. Okay. Questions on this problem? Were we done? Did we finish this? No, did I get an answer for you? Let me see if I got an answer here. 8/3. Okay, this turns out to be 8/3. So the total flux is going to be all our answers added up. And all we had was what, 2 pi from before? Right? And then plus 8/3. That's our answer. So final answer is 2 pi plus 8/3. I don't have room for it. I'll throw it right here. So to answer this, so the total flux over the entire surface of f ds, the entire thing, is going to be 2 pi plus 8/3. Okay. And that ends that section. What do you think? Stop? Keep going? We haven't even started 13.8. That leaves me one day for 2 sections. That's my... Let's at least talk about, at least start 13.8 so we don't have to go through all the definitions on Wednesday. Okay, so remember that when we had line integrals, which was this one up here, right? That the way we did it was we took the C, we found a parametric curve, and then we evaluated our vector field at that parametric curve. We dotted it with the derivative. And this was the line integral along the vector of the vector field along C, right? So we had that before. Okay, Stokes' theorem says that if S is an oriented piecewise smooth surface, oriented piecewise, oriented just meaning, again, the normals are all there. They're continuous as you move through. They vary, but they vary continuously. It's piecewise smooth, so maybe it's multiple surfaces, but each one of them is smooth. And that surface is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. Okay, so I have to draw a little picture of what's going on here. What we have is we start out with, you can look at it either way. Let's say that this is S, right? And it's got normals sticking out of it like this. Let's say that that's the orientation we have, right? If we look at that S, we look at its boundary and we look at the curve going around that boundary or around that surface and call it C. Now C is positive orientation here, right? Right, counterclockwise. S pointing up. So positive orientation, we're going to look at, we're going to move in counterclockwise, or we should say that the surface is to the left of this, right? The enclosed region is to the left of our path of travel. So as we move here, to the left is S, to the left is S the whole time, right? Our normals are pointed up. Okay, so that's the picture. This is going to tell us that if we want to do the line integral around that curve, which is going to be closed, right? Then all we need to do is the surface integral of not F, but what? The curl of F. Remember, the curl of a vector is a vector, right? So if we take the curl of this field and dot it ds, that will yield that, or do it the other way around. If we're trying to do this, we go backwards. That's what Stokes' theorem says. But just remember the curl of F, how we got the curl. the curl was del crossed with the vector field, which was that formula. Do you think we have enough time? No? 5 minutes? Ugh. Let's talk about, we won't do this problem, but let's just look at the setup of it, all right? You have, it's saying find the line integral of the vector field over this C, where C is a triangle with these vertices, and here's the vector field. So if we were to set this up, here's what we'd be looking at. We'd have this triangle, we'd have vertices here, here, here. Right, so it's this triangle in three-dimensional space, like that. And the way we would do a line integral, if C is the path around this, the way we do the line integral is what? Anyone remember how we would do this line integral before Stokes's? We would have to do R1, R2, and R3, right? And these three R's would draw the line segments going from here to here. So we'd have to find the parametric equation for that line segment, then the parametric equation for this line segment, then the parametric equation for this line segment. And remember that little ds in there also, right? Remember that, all that? So we'd have three different integrals that we'd have to set up in order to do this. And then we would have to plug in each of those into the vector field, replacing the x, y, and z with whatever our components of our curve is, or our line segment. And then we'd have to dot them, and then we'd have to do the integral. It would be a real pain in the ass to do it. All we need to do now to figure this problem out is find the curl of f, which we can compute, and integrate over the surface that that triangle encloses. So what is this surface that this triangle encloses? What type of surface is this? It's just a little piece of a plane, isn't it? And I could look straight down, and straight down from that plane is like a triangle. So I have restrictions on x and y. I have the plane, right? I could look at that plane as a surface where z is a function of x and y, and I could use that formula we just used. The great thing about this is that the curl of f is going to be something nice. It's going to be easier to work with. So that's where we're headed. I don't know, we don't have a whole lot of examples in 13.8. I only have 3 examples in 13.8. So I'm pretty sure next class you will at least see 13.9. You'll at least get the div formula. We'll do at least one problem with it. And then I guess we can talk about the final a little bit next class. Our final is on Wednesday. It's supposed to be at 12:30, which I know we normally meet at 1. But all 1 o'clock classes, their finals are starting at 12:30. Whatever, it's almost 3 hours, so 3:15. All right.